Good morning, good afternoon, and good evening, depending on where you are in the world. I am Nirosh Jayaweera from Department of Mechanical Engineering, University of Mortua. I am the session chair of this session. Theme of this session is fostering sustainable research in mechanical engineering in the new normal. It's a very interesting theme, and I would like to remind presenting authors that you will have a maximum of 10 minutes presentation followed by 7-minute question and answer session. Okay, now move to our first paper today is finite element model of PAAm hydrogel to assess optimum thickness for cushioning application under food. Authors are RMRC, Udayanandana, KMTD, Gunasekara, and P. Silva. It is my pleasure to introduce our first speaker, Mr. Udayanandana. Mr. Udayanandana is a lecturer at Department of Mechanical Engineering at KDU. He is the final stage of completing MPhil degree at University of Mortua, and his research interests include polymer-based biomaterials and CAD/CAM. Additionally, he has completed PG Diploma in Mechanical Engineering at Birmingham City University, UK. He received his Bachelor of Engineering degree in Mechanical in Manufacturing from University of Herath in 2004. Now, I would like to hand over to you, Mr. Udayanandana.
Thank you, sir, for your introduction. Good morning to all. Have you ever thought of importance of the insole in your shoe? The insoles in sports shoe and orthotics play a key role in protecting foot from excessive loads. The material and the thickness of the insole are key factors affecting the performance of the insole. Today, I'm going to present the development of finite element model of polyacrylamide hydrogel to assess optimum thickness of cushioning applications underfoot. Okay, first we will look at the material used in this research. Hydrogels. So hydrogels have a specific 3D porous polymer structure that can hold large amount of water due in this structure. Due to this specific structure, they are used in different applications such as agriculture, disposable diapers, drug delivery, wound dressings, contact lenses, and tissue engineering. So we investigated its ability to use as a material for insoles due to this specific behavior, such as relaxation behavior, cooling effect, high thermal capacity, better shear properties. But the main weakness of this material is low mechanical strength. This has to be overcome and tested if we use hydrogel for load-bearing applications. So let's see what are the maximum stresses acting on the material if we use it under the foot. The peak pressure of average healthy person can go up to 700 kilopascal. This value is higher than this for patients with history of diabetic foot ulcers. According to IWGDF guidelines, the recommended maximum pressure on foot planter is 200 kilopascal. But the available EVA insoles can reduce only up to 240 kilopascal. So the aim was to introduce a material that is more suitable for patients with diabetic related problems. But in this paper, we are presenting only the thickness optimization part of the research. So that the aim of this research is to find optimum thickness of this polyacrylamide hydrogel, and objectives include conduct the testing required for develop this finite element model, and after that we develop finite element model, and after that finally validate this. First, if we start with the experimental and laboratory practices used in this research, we measure the thickness using thickness gauge and measure the hardness, and all the material properties were tested by using universal testing machine, including the stress-strain behavior and stiffness, and also stress relaxation test to acquire the viscoelastic properties. And when it comes to finite element analysis part, commercial abacus finite element analysis software was used, and hydrogel was modeled as visco-hyperelastic material. If you look at the overall picture of the methodology, it includes the testing of the material to acquire these material properties to develop the finite element model, material model. But I am not explaining the development of this material because I have already published it in this previous paper. These details of, if anyone interested, they can refer to that paper, this development process of this material. And then the next test is test this material with the indenter to simulate the heel of a person. Actually, here we use a pressure insole. The pressure insole was kept in between the indenter and the material, so that we can get the surface pressure acting on this material. And similar thing was modeled in finite element software. Here I used 2D axisymmetric model. And also mesh independence were considered in the validation. Then this is the validation of this material, the pressure insole reading and finite element model values for 5 mm thickness were compared, and they are overlapping each other. So we can use it for further analysis. So after that, we change the thickness of this model in finite element, check the values, and you can see when you increase the thickness, the peak pressure tend to decrease gradually. So, but our requirement is, the limitation is we have to reduce this peak pressure below 200 kilopascal. So when it 5 mm, we can't achieve that. It's 205. So above 6 mm, the pressure, peak pressure, will reduce below 200 kilopascal. But there's a problem. You can't increase the indefinitely this thickness. So if you increase it beyond 10 mm, it could affect the balancing or static and dynamic balancing of the person using this material. And also cost, the cost also increase, that is another factor. So as a conclusion, I can say that the peak pressure reduction can be observed with the increase of thickness, and the peak pressure reduction below 200 kilopascal can be observed about 6 mm thickness, and the recommended thickness for this polyacrylamide hydrogel was 6 to 8 mm for effective pressure distribution. And these are the important references, and this, the last reference is the one I mentioned, that you can refer to this further details. And I would like to thank Center for Biomedical Innovation, University of Moratuwa, for providing this pressure insole in this testing process. And also, I would like to thank Ms. Chaturani Dias, research engineer, Center for Biomedical Innovation, University of Moratuwa, to helping get the reading and this processing done during this experiment. And also, as a next step, SEBI has taken this to a next level of commercialization as a product. And so I would like to thank, and this multidisciplinary approach of this research, because chemical and this mechanical, biomedical, these fields were involved in this research. So thank you very much, and you are welcome to ask any questions and use the further clarification. You can use email or chat box can be used.
Are they meant for people doing sports, or are they meant for people like us who may be having problems with our feet?
Yeah, this is specifically, so this is actually a very, that means mechanically this strength is somewhat low. So we are specifically target for diabetic related patients because their main focus is reduce the stresses. That is the usage time may be limited. If you sports, actually there are a lot of forces acting, a lot of impulsive loads acting, and
okay, so
yeah.
It's not for sport. Is this to be put inside normal shoes, or would it be too thick to put it inside a normal shoe?
So far we have developed this as a material. Then we can use it as insole in the normal shoe. Yes.
Thank you.
Thank you.
Any other questions from audience? Okay, I will ask question. Udayanandana, what is the research gap here, and what is the real innovation of this work?
Research gaps, then that's normally in the market, these available insoles, they can't reduce to the expected pressure. That's one thing. And this material has some additional advantage like cooling effect, because the temperature of the foot is very important factor in diabetic patient. So we can reduce that, and the thermal capacity also high in this material. And the relaxation behavior also different due to this specific structure of this material. These are the main things we considered in this by selecting this material.
Can you briefly tell me what is the accuracy of your APA model? Have you checked the accuracy?
Yeah, we compared. Yes, we compared it with the pressure insole values. So it's almost overlapping each other.
How many samples you got there? How many samples?
3 samples.
3 samples.
Yes.
How many time you took? Only you the one reading. One
reading 5 minutes. It takes 5 minutes. We keep it 5 minutes. The indenter.
As a comment, I recommend you to get more samples and additive results, because it is approximate model. And you.
Yeah, thank you very much.
Any other question? Any other questions from audience? Okay, if the participants have further questions, you can always ask the question to chat facility. The question will be shared with the presenter, and presenter will contact with person who asked the question with answer. Okay, everyone, thank you.
Thank you very much. Thank you.
Okay, our second presentation today is design and development of plastic waste recycling apparatus. Authors are SHMNS Herath, RJ Wimalasiri and S. Udawattha. It is my pleasure to introduce our second speaker, Ms. Nadisha Sandamali Herath. Ms. Nadisha Herath received her Bachelor of Technology Honours in Mechanical Engineering from the Open University of Sri Lanka. Additionally, she has completed HND in Engineering from Advanced Technological Institute in 2014. Currently, Ms. Herath is working as a MEP coordinator in Micro Construction Private Limited at Gunasekara. She is going her research in design and development of plastic waste recycling apparatus. Now I would like to hand over to you, Ms. Nadisha.
Good morning, all of you. I am Nadisha Sandamali from Open University of Sri Lanka. Firstly, I would like to give this valuable opportunity to me present the research in this conference. Research title is Design and Development of Plastic Waste Recycling Apparatus. First, I will do a brief introduction about the research. Let's see what is the plastic. Plastic is a man-made material. It consists of organic molecules, and plastic can be formed into the various shapes by variety of processes such as extrusion, molding, casting, and spinning. Plastic has many different uses. According to this graph, you can see in and everywhere use the plastic. Because of the low cost, easy to manufacture, versatility, and impervious to the water, plastic is very popular in the world. But there is a problem. What is the problem? For the biodegradable, for the plastic, plastic takes many long period to biodegradable. Therefore, if we dispose the plastic into the environment, it will be very harmful to our earth. Next, I will explain the current status in Sri Lanka. According to the custom figure, per month, 1,600 tons of plastic import to the Sri Lanka. From that, 30% export as a product, other remaining 70% disposed to the environment. From that, only 35% recycle, and others burn, reuse, or landfill. Next, I will explain what is the plastic recycle. Recycle is the process of recovering waste and reprocessing that material into the useful product. Aim of this research is to give a sustainable solution for the domestic plastic waste by recycling and reduce the environmental pollution that made by the plastic waste. Objective is fabricate a mechanical apparatus to melt and create a sheet from plastic waste. As a part of the research, visited one recycle factory located in BY zone in Herath. In their PET bottle, they recycle the PET bottle into the polyester yarn. But in their process, the bottle lid, they disposed as a waste. In this research, as a raw material, use this lid brush. Next, I will explain the methodology. First, collect the lid brush from that above said factory. Then do the water test. By the water test, can separate the low density polyethylene, high density polyethylene, and polypropylene. Then let the material into dry. Then apply the heat. Then melt the plastic. After melt, apply the force, and in the mold, sheet is creating. These processes including in the mechanical apparatus. Next, I will explain the parameters of the sheet. Length of the sheet is 30 centimeter, width is 22 centimeter, and thickness is 1 centimeter. What can we use for this sheet? We can use this sheet as a paper clipboard table, mats, or files, or to make any other fancy items. This is the proposed design for the apparatus. It consists with a linear actuator, 2 molds, 2 guiding rods, and 2 heating elements. By the linear actuator, move the upper mold, and 2 guiding rods guide the moving path, and heating elements give the heat. Next, I will explain how this apparatus works. First, put the lid brush into the bottom mold. Then heaters on, plastic melting. Then after 10 minutes, actuator on. Then moving down the upper mold. Apply the force. Then apply the force on the melted plastic. After 15 minutes, press the initial button on the actuator. Then moving up the upper mold. Next, I move to the implementation. As shown in this figure, made the 2 molds, upper and bottom mold, by GI sheet. Then this 2 molds set into the base, and here we use the hydraulic jack instead of the linear actuator, because of this. In this pandemic situation in the country, we couldn't find the proper linear actuator. 2 coils set into the 2 molds. Then this is the electrical panel board. It consists with circuit breaker, on and switch off, on and off light, temperature controller, indicator, and timer. And also there is a thermostat set into the bottom mold. This is the complete set of apparatus. Next, I will explain the difference between the design apparatus and implemented apparatus. Design apparatus include the linear actuator for the pressure, apply the pressure force. In implemented one, use hydraulic jack, and moving part in the design apparatus is the upper mold. In here, moving part was the bottom mold, and moving direction in here is up to down, and in implemented one, moving path was down to up. Testing of the apparatus. First step is lubricate the surface of the mold. For that, I use the silicone spray. Measure the weight of the lid brush. Then put the lid brush into the mold. Then moving up the bottom mold by using hydraulic jack. Then start the heaters on, and temperature set. Then let the plastic melt. After 10 minutes, heaters automatically off. Then apply the force on the melted plastic. Then after 15 minutes, pressure release. Then bottom mold moving down. The apparatus was tested by varying various temperature and time. The first output was not good. In the middle, it was broken. But in the 130 Celsius in 10 minutes and 120 in 15 minutes, got a good output. Total cost for the design was 46,500. And as a future improvement, I suggest suitable cooling system can be added for the system to get rapid cooling. And if we add the pressure gauge to the system, can we measure the suitable pressure for high quality output. And also this system can be made as a fully automated system by using a linear actuator instead of the hydraulic jack. And if use the design heating element, can be get a proper heat conduction through a surface of the mold. These are my references, and I would like to express my special thanks to Dr. Wimalasiri and Engineer Supun Udawattha, who helped me and guide me always. And also I would like to thank the staff members in mechanical department in the Open University. And further, I would like to thank Engineer Tharadideniya and Mr. Sisira, who was helped me to the fabrication process. And finally, I will thank to all who helped me in various ways to success this research. That's all about my research. Thank you all of your kind consideration.
Thank you, Ms. Herath. Any questions from audience?
I have a couple of questions. One, I think when you said plastic, I was thinking it was about all types of plastic. You are limited to lids, which are very clean ones. Is the amount of lids a large quantity, making this a worthwhile project? First question. Second question, your approach seems to be more trial and error. You tried different temperatures and then said, what is the best? Did you not try to do for different temperatures and measure the strength of the output and then plot a graph? Okay.
Once I checked the that final output strength of the final output, it was 16 megapascal. Not do so many tested for this sheet. Do one tested.
Now, if so, why did you have defects? Well, if you did the design correctly, I would not have expected defects with such large holes and things like that. Okay, no further questions.
Any other questions from audience? Any other question from audience? Okay, I think your design having some issues because you have applied hydraulic jack. Hydraulic jack produce center load. Okay, then you will get maximum pressure on the center. I think that is why your final output having defects. Okay, it will produce more pressure at center, more force. My question: why you select center load? Like, have you done any concept models? Have you done a concept model? Why you select this design? Oh. Any other alternatives? Any other alternative design? Why did you select this final design? I would check other options. Did you get my point? Your design.
Can I ask the same thing in a slightly different way? Now, when you do a project like this, I think it's a good project, but you should have done a preliminary model and on the computer checked all these before you actually started constructing. Then you won't have come out with these problems. Did you do any modeling before you started constructing it?
I tested a small sample by heating by using
No, I'm not talking about testing, because testing
Analysis part.
as an engineer, you should first do a theoretical analysis and find out the best. The idea is good, melting and doing that, but the best should be obtained by doing a first analysis. And as Professor Jayaweera mentioned, where should the pressure come? How will that affect the strength? All those should have been analyzed. So I would suggest that you continue your project by doing that part.
The next question, how do you select the materials?
Because
Any justification?
in
Apparatus material, I mean.
Did you ask in the GI sheet?
Yeah, GI sheet, what is the
GI
length,
sheet,
what machine size, how do you select this type of machine, what the material, why did you select GI, why can't you go for other materials?
GI has some, not, it's like the plastic, because it has some lubricators. The plastic not melt in that GI sheet other than others.
Corrosion issues in future. So we'll expect corrosion issues because GI mean apply additional coating. Okay, if that coating damage, the stuff may corrode. You should have proper analysis. Why did you select this material? What are the alternative materials? What are the manufacturing process you can use? You have to analyze first and make the final first. First, you should have a concept model, different concept model, and select best final model based on your strength and weaknesses. Then you can build your final prototype. Okay, end of my question. Any other question from audience? Or otherwise we will move to next presenter. Thank you, Nadisha. Thank you.
Oh, thanks.
Okay, then we will move to our third paper today, is performance analysis of a photovoltaic system under different configurations. Authors are FBYR Silva, RMPS Bandara, and RA Attalage. It is my pleasure to introduce our third speaker, Mr. FBYR Silva. Mr. Randana Silva obtained his BSc Engineering in Mechanical Engineering from KDU. He is an associate member of IASL and associate engineer at Engineering Council, Sri Lanka. He is currently serving as a lecturer in the Department of Mechanical Engineering. His teaching area include applied mechanics and machine design. Now I would like to hand over to you, Mr. De Silva.
Thank you, sir, for the warm welcome. The research topic is performance analysis of a photovoltaic system under different configurations. The presentation is categorized to these following figures. First, we'll talk about the introduction, then the working principle of the solar cell, then the research objectives, methodology, analyzed results, finally, the conclusion. References is also indicated. Now, under introduction, solar energy is used worldwide as energy can be harnessed directly from sunlight. Currently, the photovoltaic panel is consists of one of the fastest growing renewable energy technologies that plays a major role in generating electricity. Now, when it comes to solar panels, you have polycrystalline solar panels as well as monocrystalline solar panels. Now, in your screen, you can see in the figure number 1, you can see the two types. And also, the lattice structure is shown in figure number 3, where the monocrystalline solar panel contains a fully set lattice structure, where the polycrystalline solar panel is uniform on the grain itself. Now, there are some advantages as well as disadvantages in these two types. Now, when it comes to the efficiency or the sensitivity for the irradiance values, the monocrystalline solar panel is further up considering the polycrystalline solar panel. Now, let's say the planting area is kind of small and it is subjected to some shady environment. Then, of course, you have to go with the monocrystalline solar panel, because otherwise the power output will be much less. But if it's not the case, you can go with the polycrystalline solar panel, because manufacturing cost is high with the monocrystalline solar panel. Okay, now let's say our power output of the solar panel system is 1 kilowatt. Now let's say we want to increase it up to 2 kilowatt. The normal system is to get another set of panels and to couple with the existing one. But in this research, what we are mainly suggesting is, without going with the additional set of solar panels, we can obtain the same power output while by using a mirror system or else a concentrated photovoltaic system. So the price will be much less. Now, when it comes to the CPV system, the concentrated photovoltaic system, we are going to increase the irradiance values that are going to fall on the panel itself. Now, there are some advantages as well as limitations when the irradiance values become too high. So the limitations are the panel temperature itself tries to increase. Now, when the panel temperature increases, the efficiency of the panel tends to go down. But in this research, what we have come across with that particular issue, and we have made a remedy by introducing a cooling system so that the panel temperature will be maintained properly. Right. Now let's see the working principle of the solar cell. Now, in your figure, in your screen, you can see the figure number 4. Now you have the solar cell, you have the topmost layer, and then the bottommost layer, and then the intermediate layer, in between layer. Now the top layer is made mainly with silicon and small amount of phosphorus, giving a small amount of negative charge. And then the bottom layer, it is mainly made with silicon and added a small amount of boron, which gives a small positive charge. And then photons comes and strikes the panel, and it penetrates and it reaches the middle layer, right? Now, when the photons reaches the middle layer, the electrons absorbs energy and it jumps, creating a hole. So these electrons tries to move to the top layer, creating a negative charge, and then the holes moves to the bottom layer, creating a positive charge. So there will be a negative charge on the top, a positive charge on the bottom. So the panel cell itself acts as a battery. So if we couple the top layer with the bottom layer, there will be a flow of electricity. Right. So let's see the research objective. Now, in this research, we are going to measure the normal power output of the conventional solar panel. And then we will be introducing a concentrated photovoltaic system with a mirror system. And as for the mirror system, we have gone with a concave mirror. And then we will measure the power output generated by the set panel. Now, I told you that when we are using the CPV system, the irradiance values will rise, the amount that falls on the solar panel, and then the temperature will rise. So then at a certain point, the power output will gradually drop. So as a remedy, we have introduced a cooling system. Now, cooling system is also can be categorized into two. that is active cooling as well as passive cooling. So if you go with active cooling, there will be some additional energy source that we should use. But in this research, we have gone with the normal passive cooling, where no any additional energy is required. And then finally, we will compare all the set configurations. Now, under the methodology, we have 4 types of configuration. Configuration number 1, without any modification, we will be calculating the power output of the solar panel. Now, this we have used the monocrystalline solar panel. And configuration number 2, we are going to introduce the CPV system, the mirror system, and then we will measure the power output. Configuration number 3. Now, I told you that dissipating heat, we are using a passive cooling system. So passive cooling system also we can we have divided into 2, that is air cooling system and then the water cooling system. So configuration number 3, we are mainly focusing on the air cooling system without having a water cooling system. And then configuration number 4, we are going to introduce air cooling incorporate with water cooling as well. So you can see in the 4th figure, this is the bottom section of the solar panel. We have used a water cooling system, and then to increase the surface area, we have used fins. So air cooling will also be done incorporated with water cooling mechanism. Now let's talk about the temperature distribution. So I told you that the temperature will also gradually rise with the higher intensity of irradiance values. Now we have made sure that the temperature is properly distributed without creating some hotspots. So we have initially measured the normal panel temperature distribution, and we have identified some of the hotspots. So when we were creating the water cooling mechanism, we have focused on those areas, and we have evened out, or we have evenly distributed the heat distribution. Because the problem is, if you have a couple of hotspots, in time to come, the panel will degrade, right? And also in the 4th figure, you can see we have the reservoir, water reservoir, and then we have the panel, and then we have the concave mirror system. And then underneath, we have used fins to accommodate air cooling. So we have in 4th figure, we have air cooling, water cooling, along with the concentrated photovoltaic system. So these are the measured results that we came across when using configuration number 1. Now, these results are without any modification to the panel. So this results gives a clear understanding about the normal power output of the solar panel. So now you can see, if you have a close look on the time, the surface temperature, the maximum surface temperature rises to about 60 degrees of Celsius. And then the maximum power output of the normal conventional solar panel is 288. So you can see the graph also. And from 800 hours to 12 noon, there's a gradual increase. And then after 1 o'clock, at 1 o'clock, it reaches the maximum value. And then you have a drastic drop under the configuration number 1. Now let's see what are the values that we got under configuration number 2 with reflectors, and this is without cooling. So here from 800 hours to 12 noon, there's an increase, but the increase is not that much, right? This area. And then it reaches a maximum value of 454 watts, and that is at 1 o'clock. And also you can see the maximum temperature of the panel reaches about 67 degrees of Celsius. So that is too high because when the temperature reaches high, the efficiency of the panel moves down. And now we'll see the measured results with configuration number 3. Now this is with reflector and air cooling. So here we were able to maintain or else to reduce the temperature, average temperature to about 56.2 degrees of Celsius. And then we were able to reach a higher value of the power output, which is 456. So from 800 hours to 12 noon, there's an increase, but increase is not that drastic. But then again, like after 1 o'clock, there's a definitely when the irradiance value is lowers, the power output will also gradually it will decrease. But there's no any drastic drop. So configuration number 4 with air cooling and water cooling, we were able to reach a maximum value of 456. So if we compare all the figures, what we suggest is from 800 hours to 1130, we can go with the normal conventional panel, and then we can introduce the concentrated photovoltaic system. And also you can see with this graph, if we don't go with the cooling system, the panel power output will drop. But if we incorporate the air cooling and water cooling, we will be able to maintain a higher power output. So that is what we are saying in this research. From 800 hours to 12 noon, we can go with the normal conventional power, conventional panel, and then we can introduce the concentrated photovoltaic system. So these are the references that we came across, and thank you. And I want to make a special thank to my supervisor, Dr. Bandara sir, for guiding me throughout the project. Thank you.
Thank you, Mr. Silva. Any questions from audience?
I have several. First, were the measurements all made on the same day or on different days? And on how many days were measurements made? Why I ask that is, I'm also doing a lot of work on solar, and I know from day to day, the variation of solar patterns are completely different. Therefore, when you talk about morning and afternoon, because you can get on a very bright sunny day, you can get a curve which is purely sinusoid. I've actually got it. So saying that the normal panel has less in the morning and more in the afternoon is not valid unless you particularly told me what day it was, whether it was a cloudy day, whether the comparisons were made on the same day.
Yes, sir. That's a good question. Yes, we have taken these values for about 3 months' time, and I know that is not that much. If we,
so when you were presenting, you should have said these are the average of this reading. Are these the average of this reading? And were the we have 4 configurations. Were the 4 configurations done simultaneously, or on one day you do one configuration, on another day you do another configuration?
Yes, sir. It is like this. Now, it is mainly based on the cloud coverage. So, cloud coverage we can set as clear skies, few scattered.
No. That doesn't work. That doesn't work. Because if you want to talk about whether morning or afternoon, the dental classifications don't work. Because you are talking and saying that morning, there's no difference like that. So if you take different days, you can't actually say that. Otherwise, what you should have done is you should have taken a standard output. For example, standard solar cells, manufacturers, you can monitor the output. So if you showed the output from a standard one and then compared with your one, and then for each one compare that, then I would have accepted this. Otherwise, to say that at certain times, then the other one is when you put a mirror, you're going to block the light. Therefore, your conclusions that in the morning it is better not to have it or something is not valid, because your direction of your mirror would have been such that it was blocking the sunlight or something like that. So all those should have been taken into account.
Yeah, that is true, sir. So we can like increase the what do you call the validation of the results if we have 4 panels which is being measured simultaneously.
Yeah,
that is true, sir.
But I don't accept your results because you have not validated it.
But sir, now if we go with the normal irradiance values, let me share the slides again. like here. Give me 1 second. So here, if you look at these irradiance values, so these.
From where do you get these values? Did you calculate them, or did you get it from?
We measured it, sir. From the Ratnam airport, from the meteorological department, we measure these values.
Okay. So you got. You should have said that. Because,
yeah.
Because when you are explaining a curve, then you should have said you were comparing with the values from the Ratnam airport or something like that. Otherwise, you were not talking about real comparisons. So that was what I was talking about. There should be some standard against which you are going to compare. Okay. So what about the second question about the mirror? Would be on one side or on all sides?
It was early on the one side, sir. That was the problem. Now from 800 hours to 12 noon, like you said, the reflect what do you call the shade of the mirror comes to the panel itself. So that is why the power output has dropped for configuration number 2, 3, and 4. But then again, after 12 noon, the power output was high. So that's why what we are saying is to use the normal conventional solar panel from 800 hours to 12 noon, and then you have to incorporate the less water cooling.
And now remember, either you're thinking of large scale or domestic. If it's domestic, changing configurations is not satisfactory. Otherwise, you can even ask people to rotate the panel and you can get very much better results. Now, I think the direction you have kept is probably horizontal, not at 7 degrees. Well, if you keep it at 7 degrees, the peak occurs at about 11:30 or 12 and is symmetrical. Now, your one was something like 1 o'clock, probably because the panel was not oriented in the optimum direction.
Yeah, that is true, sir.
Okay. Okay, thank you.
Thank you, sir.
Okay, any other questions from audience? Any other questions from audience? Okay, I will ask, can you tell me what is research gap here in this research?
Yes, sir. Now if you see the normal available solar panels, they are not mainly focusing on the cooling system. Now in earlier studies, what they do is sometimes they spray water on top of the solar panel just to make it cool. But in this research, what we are mainly focusing on, we can go with a cooling system, with the air cooling system as well as water cooling system incorporately, and we can heat the water simultaneously, and then there will be a properly the temperature distribution. So earlier I showed there are some couple of hotspots being generated on the solar panel itself. So we can eliminate those hotspots and we can go with a higher
FEA model, you mean?
Sir?
FEA model.
Yes, sir.
Yes. FEA model.
Yes,
okay.
Yes, finite element model. Yes, sir.
Yeah.
So those hotspots can be eliminated and we can expect a higher lifespan of the solar panel itself.
How do you check accuracy of FEA model?
FEA was done, we measured the peak temperature distribution value, sir, because the highest power output.
No. Because I'm asking how do you know your FEA model is accurate?
Can I ask a similar question related to that?
We measured it.
Now, if you have, now for example, the one I'm talking about is 12 panels. The output of the 12 panels, although they are supposed to be the same, there is about 10% difference. So the temperature highest one may be due to differences in the panels. And in your model, you may not be representing that correctly. It may be valid for this particular panel, but for some other panel, it might be different because from panel to panel, there are differences.
Yeah. there might be some differences on panel to panel, sir, but then again, the temperature distribution, we have modeled the finite element from the finite element analysis. We have modeled the distribution as well as to cross-check the measured results. We have used a thermal gun and we have manually measured the temperature values, sir.
No further question.
Okay.
Here we have in this one, I'll show. So in this figure, sir, we have manually measured the temperature values by using a thermometer. And then we have modeled the distribution, sir. So it was cross-checked with the measured values as well as the FVA model.
Okay, thank you. We don't have any other questions from audience. I will move to next paper today. This is a final paper. Paper is review on the impact of auxiliary engine loads on the fuel economy of light duty vehicle. Authors are D. Casseer, B. Athukorale, and S. Gajanayake. It's my pleasure to introduce final speaker, Mr. Vishwa Athukorale. Mr. Athukorale received his BSc Honours degree in Mechatronic Engineering from KDU. His MBA from University of West London, UK. He also a Chartered Global Management Accountant and Associate of the Chartered Institute of Management Accountant. A certified practicing accountant, Australia, and associate member of IESL. Mr. Athukorale is reading for his MSc at University of Moratuwa in the field of industrial automation. Currently, he is working as a lecturer at the Department of Interdisciplinary Studies, Faculty of Engineering, University of Sri Jayaweera, Sri Lanka since 2018. Now, I would like to hand over to you, Mr. Vishwa.
Thank you, sir. Good morning, everyone. I'm going to present our review paper on the impact of auxiliary engine loads on the fuel economy of light duty vehicles. So as a preamble, you can say that auxiliary engine load of an automobile is a power demanding unit, mechanical or electrical power demanding unit that draws power to operate auxiliary equipment from an engine. And most of automotive auxiliary loads are belt driven. Air conditioner, alternator, water pump, and power steering pump are the major power consumers from in automobiles. So as you can see in this figure, we can see that this is from a paper published by the SAE. The auxiliary loads draw power proportionately to the engine speed. And if we take the air conditioning system, it draws around 5 horsepower at 3000 RPM, and alternator draws around 2 horsepower at 3000 RPM. The important thing to notice here is the almost every auxiliary unit we discuss here draw power proportionately to the engine speed. Also, and when it comes to the impact on fuel economy, we have taken the studies of the driving cycle test procedures of EPA US to analyze the impact on fuel economy. So if we take the individual auxiliary units again and check their fuel consumption, we can see a total fuel consumption drop as listed here. So these figures are given by miles per gallon. So if we take the air conditioner, then the operation of air conditioner causes a 1.5 gallons per mile, sorry, miles per gallon drop when it comes to fuel economy, and follows the alternator, the fan, and the power steering pump. So as discussed before, the air conditioning system is the affects the most as an auxiliary load when it comes to fuel economy. And common characteristic of belt-driven engine auxiliary unit is that their input power for operation is proportional to the engine speed. That is, the power drawn from the engine is proportional to the engine speed, but output power is not relevant to the engine speed. So if we analyze the individual auxiliary loads, starting from the air conditioning system, so an AC system comprises of the main components such as the compressor, the belt, blower, cooling fan, AC condenser, receiver dryer, inline filter kit, expansion valve, hose assembly, and the evaporator core. And if we analyze the power consumed by the AC system, so if you take the compressor output, the power is consumed by these respective loads. So metabolic load is the humans power, heat dissipation, the energy used to cool that heat dissipation, then the radiation from direct sunlight and reflected sunlight, then ambient load is the environment temperature, then exhaust load is the heat dissipated from the exhaust line, then the heat dissipated from the engine, and also the ventilation load. So if we take the Q in is the compressor drawn power from the engine, and the Q out is Q in can be expressed as the Q out divided by the compressor efficiency. Also coming to the AC power consumption or fuel consumption in different engine speeds. So this figure shows us at different speeds, including the idle stage, how the AC on state and the off state, how much more power does the engine AC on state consumes power when compared to the AC off state. So as you can see, at idle stages, an average light duty vehicle consumes 90% more power when compared to the AC off state. And the other speeds mentioned here at 50, 70, 100, and 120 kilometers per hour. And as you can see, when going to higher speeds, the ratio is lower. So we have, so this in this study, the brake specific fuel consumption is used to measure this fuel consumption impact. And also referring to the studies conducted by Kainakli and Nadamato, we can say it can be said that compressor is the most significant component affecting the fuel economy, since it causes between 77% to 89% increase in the fuel consumption. Coming to the next auxiliary unit, the next major auxiliary unit that consumes power from the engine, the alternator. Alternator is the main electric power source in a vehicle, and it is also a belt-driven unit. So if we take the electrical output of a normal alternator, so normally IC engine has a combustion efficiency of 40%, and if you take the belt efficiency as 98%, and alternator efficiency is normally around 55%, so that only gives us a 2.1 kilowatt output from a 10 kilowatt of fuel, burn fuel. Also more on the next auxiliary unit, which is the water pump. The water pump is used to for the cooling purpose of the engine. So cooling system is employed in an automobile to maintain the desired coolant temperature or the working temperature in an engine, ensuring the optimum engine operation. Usually, the water pump is driven by a crank of the engine through belt. And as for the reverse studied by Ebersol, it is shown that the water pump is accountable for around 4.5 to 5% of consumption of mechanical power generated by the engine. And also there exist various types of water pumps, mechanical and electrical to name. but a major drawback of mechanical pump is that the pump is proportional to engine speed, or the pump operates at the speed of the engine speed, but not in the proportion to the heat rejection by the engine. Also, more on the water pump, you can say that an average efficiency of a mechanical pump is around 35% to 55%, within the ranges of within the RPM ranges of 1000 idle stage and up to 5000 RPM. Also, the input power required by the water pump varies from 185 watts to 20 watts with respect to the RPM range, the said RPM range. And in an average or average operating speed of operating RPM of 3000, the power demand for a water pump would be around 185 watts. So coming to the conclusion, can be said that the auxiliary engine auxiliary loads directly affect the operating fuel economy of a light duty vehicle. And during this study, we have studied the impact of the air conditioning system, water pump, alternator, and the water pump and the alternator on the fuel economy. And out of these discussed engine auxiliary accessories, the AC system stands out to be the most impactful auxiliary accessory on the fuel economy. And if we take the percentages drawn by the total auxiliary loads, AC unit accounts for around 70% of the total power demand. Then follows the alternator, which draws around 27%, and the water pump and the power steering pump draws less than 2%. So this study was conducted as a part of our research on fuel economy prediction model for light duty vehicles. So in order to achieve this goal, we have to study the auxiliary load as well as the major components, the tractive loads. So as future work, the tractive loads must be modeled, and ultimately developing a mathematical model is the goal to for light duty vehicles. So these are the references that we have used to in this for this presentation, and the full reference list can be found in our paper. And thank you very much, and please feel free to ask any question.
Any question from audience?
Can I again ask a question? Now, when you're doing the study, now when we use the air conditioner, some will set it at, let's say, 20 degrees, some will set it at 30 degrees and various temperatures. How does the percentage consumption be affected dependent on your choice of setting?
So for this, I think we have taken the results from the Society of, sorry.
No, when you are presenting a paper, you can't talk about what others have done only. You should be able to justify what you are doing. And also, if you are presenting, it would have been better to have put kilometers per liter within brackets by converting, where nowadays that is what we use, but that's a different matter. But if you are presenting, you should also see what will happen if different people have different amounts of cooling. AC is something I know for certain times it's not operating. So your percentages are not valid. The percentage is, I think, valid at the moment the AC is operating. But at the moment the AC is off, those percentages may not be valid. So you have to look at the energy consumption as well, rather than just talking about percentages.
So may I add in some points? So when we are determining the ambient load, so we have taken the ambient temperature of around 25 degrees of Celsius. So Isha, could you go forward to the conclusion side? So there, from that, sir, we have determined this amount of the percentage, nearly 70% of the total engine input. Let's say if the engine is 100 kilowatts rated power, then out of that, this close to 7% is consumed by the air conditioning. So,
are you by any chance in Candy
Yes.
or something?
So I'm a co-author of this, sir.
I don't know. I from Candy or something? Because in Colombo, I would expect outdoor temperatures to be 31, 32 or more, not 25. But if it's 25, you don't need, hardly need the air conditioning, and this load should not have been there.
So yes.
So why did you select 25 degrees ambient and not something like 30 or 35 degree ambient? We obviously, when you are presenting it, the ambient temperature, I think, has a lot to do with the consumption.
Yeah.
Okay, can you briefly tell me what is the research gap here?
Yes, sir. So basically, what we are aiming at is we are trying to develop a kind of a estimation model for fuel economy for light duty vehicles, especially in the context of Sri Lankan traffic. So there, as a initial or preliminary study, we are planning to, actually what we have done here is to find the effect of the auxiliary engine loads on the fuel economy, which accounts about 10 to 15% of the total engine load. And apart from that, our main focus is to perform the tractive loads where the drag and the rolling resistance and the inertial loads comes in. So this particular research, the auxiliary loads will be done to formulate some kind of a theoretical basis for our final theoretical models. Yeah.
Then your engine load affect with engine size, engine capacity.
Yes, sir. So specifically, we are focusing on the light duty vehicles. So the definition comes like any road vehicle which is less than 3.5 tons. So not specifically with respect to the engine capacity, but specifically with respect to the gross vehicle weight. So yes, sir, the engine capacity would affect the fuel economy. And that would be taken as a variable for the final model. So currently, what we have done here is to analyze what kind of an impact these auxiliary loads would give to the fuel economy.
Then have you checked with this engine is operated by petrol or diesel?
Yes, sir. So currently we are focusing on the.
Show me that values.
Sorry.
Then, if you consider this engine size and petrol or diesel, that engine use, have you done analysis?
Not exactly, and at this phase, sir, we are planning to do that analysis as well. Yeah.
Planning to do in future.
Yes, sir. Because right now we have done like a review on the auxiliary loads. So we haven't built the theoretical models using this still.
Okay. If you have got any question from audience, I will wind the session. Okay. I would like to thank all the speakers for their very interesting and stimulating contribution, and all the participants for valuable discussions.